people can still because people can still join while we already start, I would like to welcome everyone to day 2 of the training school and workshop on dust aerosol detection and monitoring. We have again a very exciting program today. Before we start, I just would like to remind you on the program, what we plan today. So today we will have a focus, or we put a focus on satellite data for dust monitoring. Our speaker today is Anu-Maija Sundström, who works at the Earth and Space Observation Center of the Finnish Meteorological Institute. So welcome, Anu-Maija. And she will give an introduction to satellite data for dust monitoring. This will be around 45 minutes, and then we have again an opportunity for questions and answers. So please still use Slido for any questions you have for Anu-Maija during her talk. And then after the first part, after the first hour, we will have again a practical data discovery session where we give you a practical introduction to some of the satellite data Anu-Maija will present and introduce you to today. So again, as a reminder, before we start, because I don't want to take too much time, please go to Slido with the hashtag DUST2021. There is still, I would like to remind you also on the user requirements survey, it is still ongoing. So even if you haven't given your responses yet, please share with us your experience working with satellite data. All the material from this week, so the webinars and also the practical data discovery, are recorded and will be made available under training.eumetsat.int, and then under the training course website where you also registered. So please go there, because some of you already asked for the recordings yesterday, and we will make them available every day as they come in. Again, so how we do it with the practical training platform. So because during the webinar and during this week, the limit is for 100 people on a first come, first serve basis. But this will renewed every day. So if you haven't had a chance yesterday accessing the platform, please go there now and try to log in, and you should be able to secure one of these 100 spots today. And this will be renewed every day again. And with this, I would like, I stop my part in the introduction, and I would like to introduce Anu-Maija Sundström, who will give us an overview on satellite data for dust monitoring. And good morning, Anu-Maija, and the floor is yours.
Good morning, everybody. And thanks, Julia, for the introduction. So I will be talking you today about satellite observations of dust. And as said, I'm working at the Finnish Meteorological Institute, and nowadays I'm working with the satellite observations and air quality, but my background is in the remote sensing of aerosols. And I'm currently also part of the atmospheric composition SAF team that is led from Helsinki. So it's the EUMETSAT, one of these SAF projects, and there I'm also responsible for the training activities. So today, I think this is going to be a quite dense package of satellite observations, but I hope that then in the practicals you will learn and get to know even more in depth what the satellite actually is. So this is a very basic introduction to the satellite observations. And I have tried to now avoid as much as I can any equations or that kind of very complicated stuff. So I hope that this is more like a descriptive lecture, what the satellite observations are. So I will not go in very detailed theory of these observations. But here are the contents of the lecture. So first, some basic principles of passive satellite measurement. So I'm in my lecture now concentrating on passive instruments only. So I think tomorrow you will be hearing some introduction also to active atmospheric remote sensing measurement. Then I will go through these RGB images, what you already saw yesterday's lecture, which is really nice. So that was kind of a first taste what kind of satellite observations we have on dust. So these true color RGB images and RGB composites are kind of one group of satellite observations that actually are not retrievals themselves, but they can be created directly from the satellite measurements themselves. And then at the latter part of the lecture, I will introduce you aerosol optical depth, aerosol absorbing aerosol index, and aerosol height. So these three last parameters are then the actual retrieve parameters. So the content of the lecture goes like this. But now if we start with the passive satellite measurements, so with passive, we mean that the satellite instrument measures either solar radiation that is reflected back from the Earth's surface and the atmosphere to the satellite instrument that is in the space, or then it can measure the thermal radiation that is emitted from the Earth and from the atmosphere. So the basic idea in this passive instrument is that it doesn't send any radiation pulses or use any lasers itself, but it measures some radiation from some other source. And here is an example of a measured radiation. So a satellite instrument that measures the radiation between 300 and 800 nanometers. So the radiation spectrum looks like this. So this is the actual satellite measurement. And when we are talking about the atmospheric components, for example, aerosols, so the satellite measurements are always indirect. So satellites measure radiation, and then the radiation is converted into some more advanced parameters that describe the atmosphere. So satellites do not measure concentrations, for example, but they measure always the radiation. And then in the next slide, you can see what the processing chain from the radiation to actual atmospheric parameters is. So all of these instruments that I'm also demonstrating today, so they measure the radiation at some specific predefined wavelengths. And how then we can get information from the radiation about certain atmospheric parameters? The key here is that each of these parameters that we are interested in, for example, aerosols or different gases, they leave some kind of fingerprint to the radiation that the satellite measures. And we know the radiation, what the radiation should be without, for example, aerosols or without gases. And then based on this information, we can kind of look, this is a very simplified way to explain this, but when the satellite then measures the true radiation, so then by comparing these, what we know, what should not be there and what the satellite has been measured, so in that way we can obtain information on different atmospheric components. And so then the key is that we need to select these wavelengths that we use to observe, for example, aerosols accordingly. So we need to use those kind of wavelengths where aerosols have some kind of effect on the measured radiation. And in this figure also, what I want to show you, because these are going to be repeated later on in this lecture, so some of the terminology about the satellite observations. With level 1 data, we mean the radiation that the satellite has been measured. So that is reflectance, thermal emissivity, brightness, temperature, or some other kind of radiation parameter. And then with the level 2 data, we mean these actual atmospheric atmospheric parameters. And the level 2 data is obtained when we put in the level 1 data into a retrieval algorithm, and then after a large processing, so this computer is not what the retrieval algorithm computers look like, but anyway, it's a huge computer program, and then
there's a problem with your mic, Anumaja, or?
I think it was coming somewhere else.
Oh, somewhere else.
Yeah,
Yes,
yeah.
I was trying to look, but now it's stopped.
Yeah. Okay. Good.
Yeah.
Good. Yeah. So the basic processing of the satellite observations is that we have the level 1 data, then we put that level 1 data into a retrieval algorithms, and then we get out level 2 data, which is some kind of atmospheric parameter, for example, describing aerosols. And yesterday there was some questions about clouds and satellite observations. So now you could think, for example, yourself in an airplane. And once you are flying above the clouds, so you cannot see the ground. And that is basically the same with the satellites. So whenever there are clouds, these passive satellite instruments that uses solar radiation especially cannot see below the clouds. So the clouds kind of block the view from the satellite, since it's looking down from the space to the Earth. So it blocks the view to the ground, and we don't actually know what happens close below the cloud. There are some special cases when there, for example, might be aerosols above the cloud. So in these cases, we can get some information about the aerosols, for example, when they are above the cloud, so when the satellite can see them. Then there is also a third phenomena that I want to highlight now, since it is visible, I think, in many of the following images that I'm going to show you, and that is the sun glint. So the sun glint is a phenomena that occurs over the ocean, and that is a phenomena when the sunlight reflects off the ocean surface at the same angle that the satellite is viewing the surface. So the sun glint creates these kind of south to north stripes on RGB maps, and these, even though these look like really much like dust in the images, so don't mix these sun glint areas to dust. So that is something that I want to mention already here. Here are a selection of currently operational satellites that monitors the atmospheric composition, and each of these also observes aerosols. There are some differences how they observe. So the OMI GOEM-2 and TROPOMI observes aerosols at UV channels. So they are providing, for example, the aerosol index, whereas then the MODIS and VIIRS instruments operate also at the visible channels, and they provide, for example, the aerosol optical depth. Here is one notion, since you will be working in the tutorials with GOEM-2 data, I think. So the METOP-A decommissioning has started now as we speak, and there will be no data available after October, November, depending on the data product this year. So METOP-A will stop its operations, and it will be out of office, let's say, from now on. So METOP-A data will not be provided in the future anymore. So we will have only B and C data. But of course, the data like from last year and the years before from METOP-A are of course okay to use, but you will not get any new observations from the METOP-A. Okay, so now I'm going to show you a couple of examples of the true color RGB images that are maybe the most famous satellite observations. So whenever you are looking at the weather forecasts or you are searching for satellite images, so these kind of true color RGB images are the typical ones that you see, and most probably you also are familiar with the different features that are visible in the RGB images. So the RGB image, the true color image, means that it shows you the image like you would see with your own eyes, so it looks true. And RGB in itself, it's a technique that displays the color imagery by using the property of the three primary colors of the light, so red, green, and blue. And here I have an example of MODIS measurement. So what kind of channels from the MODIS instrument are used to create the RGB image? And so the red color is 645 nanometers, the green color is 555, and then the blue color is 470 nanometers. And then by combining the intensity information from these, so you can create the image that is in the lower right. And these images are then created from the level 1 data. So it is the radiation measurement that the satellite provides. So this is not a retrieval. This is just a combination of different channels and information, radiation information from different channels. In practice, so when you create these RGB images from satellites, so you might often need some kind of enhancement factors to some channels, but the basic idea is this, that you combine the information from 3 different wavelength channels. And here are 2 examples now of the RGB images. So in the left, so there is an example of polar orbiting satellite, so Sentinel-3 OLGI instrument. And what you get from a polar orbiting satellite is that you get observations about once per day per location or twice per day. And the observations are made always at the same local time. The advantage for the polar orbiting satellite is that you get the global coverage. So you can get within 1 day, you get most often you get with the current operating instrument, you get quite nice global coverage of it. The other example is the geostationary satellite MSG Severi. Well, here the restriction is that it covers only a certain restricted area, but we have a very good view on Africa, on Central Europe, and on Arabian Peninsula. The observations are actually provided every 15 minutes during the daytime when we are talking about the true color RGB images, so where we need solar light to get this image. So these are every 15 minutes, which is a really strong kind of advantage of this kind of instrument. So even though it does not cover the whole globe, so especially when monitoring dust storms, so this is a really good thing that we can get the observations at quite high temporal resolution. So here are a couple of images now from the RGB images of different satellite instruments, and as you already might know and have seen also in yesterday's presentation, so the dust in these kind of true color RGB images have often this kind of yellowish brownish appearance, and it's really quite easily detectable, especially over the ocean. Over the bright surface desert, it might be a little bit more difficult to detect whether there is dust in the air or not. But anyway, it has this kind of yellowish brownish appearance, as you can see in these images. And here you can see also now in the left, so you can see the sun glint. So you can see these kind of stripes that go from south to north. And these are not dust, but this is the sun glint. And the sun glint is really also quite easily detectable when you know what it is. So it's this kind of north to south stripes. And what I could also mention that typically then the anthropogenic pollution type of or smoke pollution type of aerosols often have then more grayish appearance, for example, in the upper right image. So we have the sulfate type aerosol in the south, and then in the north, very strong dust cases. So this is one way to observe from polar orbiters this dust. And then one notion that you should remember if you will use these true color dust RGB images from geostationary satellite. So the difference now to these previous images, what I just showed, these are all from polar orbiters. And so the appearance of the dust is always quite similar. But here, when we are using the geostationary imagery, so we need to remember that the observation time changes. So that means also that the solar angle changes. So we have a different kind of solar satellite viewing geometry, whether we look in the early morning, close to noon, or late afternoon. So that also changes the kind of the way that the dust feature looks like in these images. So especially when the sun is really low, it is kind of having a really long path length through the atmosphere. So sometimes these dust events might look more dramatic during, for example, early morning than it actually is when we are going to close to noon. So there is a really you should remember this when interpreting these images. So it is not necessarily so that in the morning the dust storm was worse than it's close to noon, but the appearance of these features are related also to the changing solar angle, and that's why these features look a little bit different. So that their appearance is not constant when you are using the geostationary satellites. When we have another types of RGB composites that are most often created from the thermal channels. So now we don't need anymore the solar radiation, but we use longer wavelengths to observe this dust feature. And we have loads of different kind of dust indexes that are based on, for example, the brightness temperature. So the brightness temperature, you can think that also that is a radiation measurement at the thermal channels, even though it's called a temperature, but it's a radiation parameter. And typically, these kind of dust indices are based on very simple band calculations. So you take brightness temperature from one channel and, for example, subtract that from brightness temperature from another channel. And here I will show you now one example of this brightness temperature difference. So the difference from the MODIS instrument. And that is the difference where you subtract the brightness temperature at 11 microns from the brightness temperature as 12 microns. And the dust detection is based on the spectral characteristics that the dust have in these channels. So here is an image on the right where you can see in the y-axis there is brightness temperature, and in the x-axis there are numbers that indicate the MODIS measurement channels. And now the channel 31 is the 11 micron channel and 32 is the 12 micron channel. And the orange line here is now the dust. And as you can see, so we have some kind of spectral, very small spectral difference, whether we look at the dust at channel 31 or whether we look at 32. And the dust spectral characteristics is somewhat different than what we have for clouds. So the clouds, the difference is going in another way also for snow and water body surfaces, and then with the vegetation doesn't change too much. So these kind of characteristics can be used to detect dust. And now I show you an example how this looks like. So if we start from the upper panel, so you can see the dust true color RGB. So what is now what I'm showing you about. So you can clearly see there also a dust. So this dust index doesn't necessarily bring you any additional information, but anyway, this is a good way to illustrate this. So first we have the brightness temperature for MODIS at channel 32, so 12 micron, and then we minus the brightness temperature from channel 31, which is 11 microns. And the result is that we get positive and negative values. And I have here now colored all those pixels that are positive with the colors of orange and light orange to dark red. And these are then the positive difference is now indicated where the dust is. And this is a very simple calculation. So you take one radiation measurement and subtract the other, and where you get this positive value. So that indicates that there is some dust. And as you can see, so the orange color quite nicely follow here what you can see in the RGB image. And this is a product that was already showed yesterday. So this is a very good MSG Severi dust RGB composite product. So this has also the same kind of analogy behind as I showed you now with the MODIS. So there is also the red channel is actually composed of the infrared 12 micron minus 11 micron channels. So there is also the same kind of difference used. And then the green channel is you take the 11 micron channel and subtract the 8.7 micron channel, and then the blue channel is the 11 micron channel. And with this analogy to the true color RGB composite, you create an RGB image. And as yesterday already explained, so the dust appears here now as a pink, shades of pink color. And really the great advantage of this product is that it's available night and day at temporal 15 minutes resolution and also near real time in an online service. So this is a really nice product in that way. And also, so this is also available during night because it's using the thermal channel. So we are not dependent on the solar light anymore. And you can also get forecasters, for example, can get additional info on cirrus cloud or dry and humid air masses based on this. There are though some limitations on this kind of rather level 1 dust composites overall. So the RGB doesn't indicate the concentration, so how much there is dust or what is the height of the dust. And also there might be, in some cases, there might be these color shades can vary and they are not always very constant. So sometimes the interpretation whether there is dust or not can be a little bit difficult. And then when we have especially thin dust plumes over ocean, so they might be a little bit difficult to observe. And with more detailed analysis, then it's recommended maybe to use some other satellite products. But here is the interpretation very roughly. So pink violet is dust, and then orange brown are clouds, and black and dark green are thin cirrus. So these are, here I have one animation that is showing you now the kind of the evolution of a dust storm. And this is a really nice, because this animation now covers also night and day data. So as you can see, you can get a really nice view on a dust event that is happening here, and you can also follow the dust plume. But as you can see, so during the night and day, maybe there is some mild changes in the shades of the colors, but anyway, this is a really nice product that provides a lot of information on the dust. And here again, I have shown just that maybe I was mentioning about the difficulties observing dust over ocean with this dust composite. So you can see that there's maybe you don't necessarily see so well whether it's the dust, whether there is really a pink or color or not. So maybe then combine with the information of the RGB, where you can clearly see that there is some yellowish dust over the ocean. So combining this information is a very useful way. Okay, so there was the basic introduction to the level 1 products, and now I'm going to show you some examples of a little bit more advanced, so level 2 products. So these are those products that are created from the level 1 by using different kind of retrieval algorithms. And maybe the most well-known aerosol describing parameters from satellite, and the most used parameter is the aerosol optical depth. The aerosol optical depth, AOD, often referred as AOD, is also known as AOT, so aerosol optical thickness. So AOD or AOT are the common, and both mean the same. And AOD, even though it is a kind of a very unique parameter, it is related to the amount of optically active aerosols in the total atmospheric column. So high AOD means more aerosols, low AOD means less aerosols. And the AOD can be retrieved from satellite and ground-based instruments. So tomorrow you will hear about AOD retrievals from the ground-based instruments. And today I'm going to show you the satellite part. So basically, the AOD is composed of the extinction coefficient. So extinction of light due to aerosols. The extinction is a sum of the absorption coefficient and scattering coefficient. And the AOD is then defined as the sum of aerosol extinction at all atmospheric levels. So you integrate the extinction from the surface to the top of the atmosphere. And AOD doesn't have any units. I have here now in the lower left, I have an example of measured aerosol size distribution. So this is actually a real aerosol distribution measured in South Africa a couple of years ago. And in the right panel, then you can see what is the contribution of each of the particle size to the AOD. So with this image, I want to illustrate you what I mean by when I say optically active aerosols. So if you now look at the aerosol's diameter less than 10 powers minus 1, so 0.1 microns, you can see that the concentration there is really high. But when you look at their contribution of those small particles to the AOD, you can see that there is almost non-existent or very small contribution to the total AOD. But then when we start to increase the particle size, so the contribution increases. And this is what I mean with optically active aerosols. So when we are talking about AOD, you should always remember that the AOD sees, let's say, only the particles roughly larger than 0.1 microns. So these have the most contribution to the AOD. And the smallest particles are often undetected. When we retrieve the AOD from satellites, so I said that I try to limit the number of equations, but here this is one equation that I really need to show, so because this is the basic equation for what we are after when we are doing the AOD retrievals. And this is a very simplified schematics of the AOD retrieval, but this shows the basic principle. So in the equation, we have the reflectance that is measured by the satellite. So this measurement we have. But then we need to kind of define what is the atmospheric path reflectance that includes the contribution from aerosols and molecules. And then what is the surface contribution to the top of the atmosphere reflectance. So this is the basic thing that we need to kind of define in the aerosol retrieval algorithm. So we start with the top of the atmosphere reflectance. Then we have where we do cloud screening, so AOD cannot be obtained on a cloudy scenes. Then we do some kind of Rayleigh correction. Then we do the surface correction. And finally, what we are left and what we are after for is the aerosol contribution. So what is the aerosol contribution to our top of the atmosphere reflectance? And here at the surface correction, I would need to note that there are some of the AOD algorithms that are providing global AODs do not retrieve AOD over bright surfaces. So you will quite soon see whether that algorithm provides any data over desert areas or not. And so you should select that kind of AOD algorithm that provides observations over bright surfaces too. So there are a couple of those. And here I have another illustration how the kind of what is the separation, what we are after here when we are doing the aerosol retrieval. So we have here the top of the atmosphere reflectance at the y-axis, and we have the AOD at the x-axis. And when we have the dark surface, so we can see that with low AOD, so the surface signal is also from really low, and at dark surfaces, when we start to overlay the aerosols more and more, so the top of the atmosphere reflectance also increases. So you can see here at the lower panel of these boxes, so when I have a dark surface and then I overlay aerosols, so the top of the atmosphere reflectance, so the image, the box seems a little bit brighter. But with bright surfaces, so then if there are no aerosols, the surface is bright, so the top of the atmosphere for bright surface is already high. And when we add aerosols on top of bright surface, it can actually a little bit darken the whole top of the atmosphere, so the top of the atmosphere reflectance can a little bit decrease. So this is the things that we need to kind of recognize. So the basic problem in the aerosol retrievals is that we need to separate these different components and find out the aerosol component from the top of the atmosphere reflectance. An important factor related to AOD is that it is wavelength dependent. So often these AOD products are given at 550, 555 nanometers, but there is really a difference at which wavelength you give your AOD. So as you can see in the lower image here, I have an example from actually a ground-based measurement, but this shows a really nice the spectral dependence of AOD. So at 1.6 microns, so long wavelength, we have AOD much lower typically than what we have at shorter wavelengths. And with this kind of spectral information also, you can make some rough interpretations of the aerosol type, actually what is present. And here is actually a dust case. So we see an abnormally high AOD at longer wavelengths also. So the typical for dust is that it is also visible in these long wavelength, long wavelength AODs. Okay, so AOD from passive instruments also doesn't indicate what is the vertical distributions of aerosols. So if you have now vertical distribution, so the AOD can be the same for two very different cases. So you can have, for example, urban aerosols close to the surface and the AOD equals 0.5, or then you can have, for example, over ocean sea salt, and then on top of that a kind of a thin dust layer, and there also the AOD equals 0.1. So this is also one thing that you should remember, that we don't have any information here on the aerosol vertical distribution. So there might be multi-layered aerosol cases or then single layer, and the result of AOD can be the same. And so the same AOD can be obtained for very different cases. So as I already said, AOD is available from several instruments. I'm going to show you examples of a couple of them. Maybe one of the most used is the NASA's MODIS instruments on board Terra and Aqua instruments. And now I have here plotted a 1-year average of in 2019 from MODIS Deep Blue algorithm. And now this Deep Blue is the algorithm that retrieves information over the desert areas too. So if you are interested in AOD over desert from MODIS, for example, or VIRS, so use the Deep Blue algorithm. And where we can see elevated values, so we can clearly indicate, we can clearly recognize some different types of aerosols, even though the AOD value itself doesn't tell you what type of aerosol we have. So we have biomass burning in the north, then over Africa we have biomass burning also, but also a very strong dust component, and also in the Taklamakan and Gobi desert, so we have the dust component present, and then India and China has the large anthropogenic pollution component in AOD. So here I show now one example of AOD at 55 nanometers from VIRS instrument. It's obtained in June this year. And what I wanted to show this image is to show you a couple of typical features, what quite often happened when we use AOD for observing dust. So typically these AOD images are quite rippled, so they are quite scattered. So you can see that there are holes in the fields. But anyway, in any case, this contains a lot of information. So AOD is the only parameter from the satellites that contains the information about the amount of aerosols. And therefore, this is very useful, even though you would not get coverage of the whole plume. So AOD, as I said already before, is not retrieved for cloudy cases. And now in the cases of very thick dust plumes, the AOD algorithms can also interpret that dust plume as a cloud, and therefore we are not obtaining AODs typically over the thickest parts of the dust, and that is something that you should kind of remember. So that the fact comes from the that the AOD algorithms need to see also the ground. So if the dust plume is so thick, so it actually blocks the view to the ground, and that's why the AOD cannot be retrieved. And also AOD is not provided at sun glint, so you can see here on the left, so the start of the sun glint above the dust plume. So AOD is also not provided over those areas. But anyway, AOD is very nice view to get an estimation of the amount of aerosols in the different parts of the dust plume. And even though there is a very little information, there is still some information. So even though these AOD images can be very scattered like here, so it still contains information. I have here now an example image of the PMAP AOD. So this is the composite of multiple instrument, multi-instrument AOD product provided by EUMETSAT. And why I wanted to show an example of this is that in the upper panel, you can see the AOD. So there is quite nice distribution of AOD again over the continent, but then over the ocean, there are the image is very scattered, and this is partly due to the clouds that are there that disturb the observation of the AOD. AOD is perhaps the most sensitive parameter to clouds. So it is the gas retrieval, for example, can allow some cloud presence, but the AOD not at all. So that this is very sensitive to clouds. There are in the AOD files from various satellites, so there are often also some nice byproducts or kind of products that are retrieved and provided in the file that can be useful, for example, to determine the aerosol type, which is not straightforward only from the AOD values. And here I show you now the PMAP aerosol class plot. So it's the same plume here, the same day, and I have plotted here the aerosol class. So in this PMAP AOD product, there is aerosol classes that are used to retrieve the AOD. So number 1 means coarse mode, 2 is thick smoke, and 3 is now the dust. So the yellowish color here. And as you can see, it quite nicely actually shows us the dust plume. In this image, I have now colored the number 6 as a combination of several classes, 10, 11, and 15. That means that there is aerosol contamination by clouds or no classification available, etc. But this is a kind of a nice way also to get the confirmation that, okay, we have high AOD. Why do we have it? Okay, it seems that it's most likely dust. So this is a nice example of that. Okay, so then a couple of other aerosol parameters still from the satellites. So what we can obtain from the level 2 products. So first here is the absorbing aerosol index. And this is now something different from the aerosol optical depth. So this also has multiple names: AI, AAI, UVAA. The UV aerosol index comes from the fact that this index is calculated using the UV wavelengths. So only those satellites can provide this aerosol index that has the measurement channels at somewhere like 340 to 400 and in that region. So those instruments include, for example, GOM2, Tropomion Sentinel-5P, OMI, and OMPS instruments. And the special feature of this aerosol index is that it is sensitive only to absorbing aerosols. So those aerosols that show some kind of spectral response at the UV wavelengths. That means smoke, volcanic ash, or desert dust. So the further distinction of these absorbing aerosols is not possible to do, so you need maybe some additional information, but it shows you the presence of the absorbing aerosols. And the AAI retrieval, it basically separates the spectral contrast at 2 UV wavelengths caused by aerosol extinction from that of the other atmospheric and Rayleigh effects, so the molecular scattering. And the strength of this aerosol product is that this is not sensitive to clouds. So there is also this aerosol index can also be obtained for cloudy scenes when the aerosols are on top of clouds. So this is the strength of this AAI is that it is not so sensitive to clouds, and this is a very good way to look at the extent of how wide the dust plume is, and the AAI is a good tracer, for example, then these dust events. There are the interpretation of the absorbing aerosol index is not very straightforward, so therefore I have now a couple of slides and things that I want to highlight when you use this product. So first of all, in this image, we can see that there are both real aerosol features and then, let's say, fake aerosol features. And with the fake or false aerosol features, I mean the sun glint. So the sun glint, if it's not filtered out, it will be showing in these AAI images as from the south to north stripes, and these are not aerosols. So in your plotting, so you will need to always filter out the sun glint, and then you will get the correct aerosol signal. And then you can see that the desert dust and also the smoke appears as elevated positive values of AAI. So positive values of AAI indicate the presence of absorbing aerosols. When we have clouds, so we can have some slightly negative values or close to zero. And also, as I said, the sun glint also creates these false positive values over ocean. So this is something you should remember when working with the AAI. And for the aerosol plumes, we typically have the threshold. Well, this is not an official threshold, but this is a threshold of 1. Therefore, that the background, as you can see also in this image, is slightly positive. So the background value where we don't have absorbing aerosols have typically values between 0 and 0.5. So therefore, we define quite often that the above 1 values are those that are, we think that are from the absorbing aerosols. And there again, we have the instrument that provide the AAI. So I have here now is the important thing, what is when it comes to the interpreting the AAI values. And since the AAI values depend on various factors, comparing different cases with each other, it's not straightforward. So this is not a direct measure of aerosol loading. So the AOD is the parameter that directly indicates you how much there is aerosols, but the aerosol index does not indicate directly whether there is a lot of aerosols or not so much aerosols. And I will explain why. So with AAI, you typically see an elevated plume, and therefore also with AAI, it's really difficult to make any interpretations what is the air quality, for example, close to surface, because it might be that the AAI actually misses the plume when it's close to surface, and it starts to kind of show the plume when it's a little bit elevated. And so for this parameter, always I recommend you to use some model in situ or LiDAR observations or aerosol optical depth or something together to kind of make the correct conclusions. And here is one image that I wanted to now show about why comparing the two cases are very difficult. So I have here like different lines, purple, blue, and yellow line. So they are the aerosols at different heights. So this is absorbing aerosols at 1.5 kilometers height, and the yellow line is then the absorbing aerosols at 6 kilometers high. And now if we look at the optical depth of 1, so we have the same amount of aerosols. If the aerosol plume is at 1.5 kilometers, it gets the aerosol index value of about 2. But if we have the layer higher above, so upper in the atmosphere at 6 kilometers, so the aerosol index gives the value of 6. So that means that the aerosol index can increase only by that the aerosol amount is not increasing, but the plume is rising upwards. And that's why the comparison of different cases is really difficult, because you would need to know also the height of the aerosol layer. And here you can see an example now of, again, the same case. So 7th June this year of COM2 AC SAF product. So COM2 absorbing aerosol index. And as you can see now, as compared to the AOD figures, you can get now a little bit more complete view on how wide actually the dust plume is and where there is elevated dust. And here is again a comparison of AOD and AAI. So again, the same thing. You can see that the AOD is really scattered image here and doesn't show the whole extent of the plume, whereas then from Chopomi, for example, we can get the positive values here, and we can see that actually the plume is much wider than what AOD now lets us believe. So combining information from AOD and AAI can give very much more detailed view on the dust plume, and AOD is the one that gives you the information on aerosol loading. And so this is always also recommend that you combine information from several observation types. And why not to add also here the dust RGB composite or the TrueColor RGB. And the last product that I'm going to introduce very shortly is the absorbing aerosol height, which is relatively new product, also provided from COM2 instruments and by AC SAF. This basically can give you the height of the absorbing aerosol layer. but there are several restrictions, so we need to have a strong enough signal, and therefore with this aerosol height you can get that only for cases where we have a lot of dust. So there really needs to be a lot of dust or the dust at quite high elevations to get a reliable estimate from the absorbing height. The AAH is also available from tropomy instruments currently, but this is also an additional information about the absorbing height or the height of the dust plume. As I said, so the AAH can be retrieved only when the signal is from the dust plume is high. So here you can see, here is the same case again, the 7th of June. In the lower image, you can see the AAI image for the dust plume, and I have circled here the area where we see the strong signal from the dust plume, so the index values are large. And for those pixels, there is the AAH, so the height of the aerosol plume is retrieved, and it gives you an estimation of about 2 kilometers here, and closer to the coast then a little bit higher values. So often with this is a very typical feature that the height information is obtained only a number of pixels and not nearly the whole plume. But anyway, this is again additional information. So take home messages from this quite dense package now of the satellite observations. So these passive satellite observations provide various parameters that you can use for monitoring dust events. The TrueColor, RGB, and composite images are available at several web services in near real time, so they are very easy to use. You don't need any kind of downloading data or anything, so you can just go to the web services and look at the data. But you should remember also so that the interpretation is not always very straightforward. So they might be like the changing color shades or these kind of things, for example, over the ocean, when the interpretation is not very easy. So then, of course, using some other products could be a useful addition. Aerosol optical depth is the parameter that provides an estimation of the amount of aerosols, but it is for all aerosol types. So high AOD doesn't mean dust AOD. It means that there are some type of aerosols, a lot of them. But then you need additional information to confirm whether it's coming mainly from dust or from other sources. The absorbing aerosol index indicates that there might be dust or smoke or volcanic ash present, but then the further conclusions on the amount of aerosols is really difficult, and therefore it's recommended to use this information with the AOD, for example. And also we can get some kind of estimation of the height for these dust plumes whenever there is enough signal, so there is a really strong signal, so we can get a reliable height estimate. But overall, I would recommend that whenever you use these satellite observations, so most often you kind of get the best view when you combine the information from all sources that you can get. So very comprehensive view on these dust episodes can be obtained by combining these observations from RGB, AOD, AAI, and AAH. So combining these can give you a quite nice analysis on different cases. Here are the end of my actual slides. I will just show you that I had in the web page, there is this version of PDF version of this lecture, and I have here collected some resources where you can go and see these online services, for example, these RGB images, etc. So you can find if you download this presentation from the course web page. So thank you.
Thank you, Anu-Maija, for this very comprehensive, but as you said, also like very informative session. So we have a bit of time for questions, and we have many questions on Slido. I will stop sharing your screen, Anu-Maija, and start sharing my screen with some of the questions. We probably will not be able to go through all the questions, but Anu-Maija, if you are fine with it, you could go to Slido and to the questions we haven't we weren't able to address, you could maybe also add a response this afternoon, if this is fine.
Yes.
Okay. So then we would start with the first question. RGB image shows us only dust or dust sand. Why we call it dust RGB image and not dust sand RGB image?
Okay, so I think this is just coming from my history past in the aerosol community, aerosol remote sensing community. So we can, so the dust and sand, the definition is the kind of the size that this describes the dust and what is sand, and it shows everything. So I mean, in the aerosol remote sensing community, we often call dust as a, let's say, it's an kind of a overall naming convention, even though it's not scientifically accurate. But it's a dust. With dust, we mean actually dust and sand RGB images, and so, yeah.
Okay, good. So then the next question is, in which level dust RGB image shows us the concentration of dust sand, above the ground or in MET atmosphere level or the higher level?
So with the RGB images, you cannot get an accurate estimation of dust loading, so the amount of, so you would need some other parameter. AOD is the one that tells you how much there is, so about the estimation, even though AOD is not the concentration, but it is connected so tightly to the concentration that you can use AOD as an indicator of concentration of dust. But actually, so because the RGB images, and especially the RGB composite, so which is created using thermal channels, so it is based on the, let's say, temperatures of the or emissivity temperatures of the dust. So it's not you can basically, you should use these RGB images to indicate where the dust is. Of course, when it's a strong episode, you can get the more clear signal and it's more pink in the images, but to actual concentration, so you should use a model or ground-based measurements or AOD as a first indicator or something like that.
Okay, thank you. Then the next question comes from Michael. How come the dust RGB includes daytime? Are the channels not sensitive to solar reflection? Yeah, so the dust RGB, so the dust RGB composite, which is created from the brightness temperature, so it is thermal channels, so no solar radiation. That is kind of that's how it is created. So it's based on the dust spectral features in the thermal channels, and then, but the true color, so what we see by our own eyes, so that is then using the solar radiation channels. So the thermal channels are not using the solar reflection at all. So they are defined so that they are at so long wavelengths, like over 10 microns. So they are at the thermal. So there is basically the RGB might be a little bit misleading, because the RGB, so with RGB true color, I mean the solar channels that are available only daytime, and the RGB composite or the dust indices, so they are from the thermal channels that are available during day and night. Okay, then the next question from Christian. Would it also be possible to get an example for dust aerosol detection from spatially high resolved data, for example, Sentinel-2? Yeah, I think, well, I haven't used Sentinel-2, so I know that it has really high spatial resolution. So often what it comes basically with these internet services that are now up, so you would need some kind of expertise in handling the Sentinel-2 data, but I'm sure that they would find some channels that are suitable for the dust detection and small scale dust detection also. So but I was now concentrating on these most kind of commonly known, and also those products that are now available on internet services and easily to access. But of course, these all the products that I was now showing are having more or less quite
coarse spatial resolution. So if you really need to know something like a really high local resolution, really high spatial resolution, so you might need to take a look of Landsat or something which is available, for example, EO browser, and there try to kind of detect the dust.
Okay, thank you. Then there's another question. I would be interested in dust and aerosols from barren areas such as mines and other open pits.
Yeah, but I have not kind of experience on this, but I would assume that you would see something. But for those, you would need to use very high resolution aerosol observations, for example, from depending on the year, what you are interested in. So MODIS 1 kilometer product, so the MAIAC algorithm, or then the MODIS 3 kilometers product, or then the VIIRS. I think it's even below 1 kilometer, the some of their products, intermediate products. So you would need to go high resolution product and maybe look at a little bit longer time period, or so then I think it could be possible to observe this.
Sorry, okay. The next question comes from Kwabena. Please, is there any geostationary satellite focused on West Africa?
Well, there is the MSG Severi is the geostationary satellite, so it sees the whole Africa, and actually I think the Africa is covered really well there. So that's, of course, there is that the spatial resolution might not be so good, but we will also in the future we will have other geostationary, for example, Sentinel-4, which will be launched in some years. So there will be new possibilities.
Okay, then I would go more maybe for, I don't know, to here. So from your description of AOD, does it mean AOD is more of particulate matter estimate?
Yes and no. Yes, in a way, yes, that AOD is the only parameter that describes really what the concentration of the aerosols might be. But I would underline, estimate. So the AOD has the contribution from all aerosol sizes, whereas when you have, for example, PM10 or PM2.5, they have the specific size where they cut the concentration, so PM2.5, so it's only particles below 2.5, and so therefore AOD is in that sense different, that you cannot cut AOD like, okay, I want AOD only from particles that are below 5 microns or something like, or below 10 microns. So that is not possible to do with the optical measurement. So you don't have any physical particle size where you can cut the AOD in pieces, but it is also true that very often AOD correlates with PM10 and PM2.5, even though it's not exactly the same.
Okay, thank you. I would take another 2 questions, and then you see already like we have 16 questions on Slido, so you can then respond to the questions on Slido. Maybe we take this one. Thanks a lot for your presentation. Could you please provide some papers, but this is just a proposal, to provide some papers, theoretical background applications for the Severi dust RGB or other useful links?
Yeah, I think there is a very nice fact sheet provided by EUMETSAT. So it's at the EUMETSAT site. So if we can get that link to a course webpage, so we can put it there. But it's a really nice condensed package of PDF of 2 pages or something, and it's really like how you use and what is really the theoretical background. So very shortly written there. So
this will be actually linked in one of the notebooks today. So
okay, great.
We can then open it and show this fact sheet.
Yeah.
Yes.
Yeah.
And okay, so then and then one more. Could you also determine the nature of the dust? If it is gypsum, carbonate, or even serpentinite, could you translate AOD to PM via some algorithms?
Yes, so the last question, yes, there are many, that is actually a quite hot topic currently in the aerosol retrieval community and satellite retrieval, so that converting AOD to a machine. For example, there are now many this kind of developments in machine learning, so that you would use machine learning to convert AOD to PM. So that is a field of research that is evolving all the time, and there are already nice products available in the web if you Google AOD to PM. So that is, but again, that is an estimate. So I would again underline an estimate here and not as a kind of ground truth. The nature of the dust cannot be determined with the satellite observations, so they are too coarse and do not provide enough information to retrieve the type of the dust. So maybe based on the origin, maybe you can make some kind of guesses, so whether it's originating from Sahara or somewhere else. Yeah.
Okay, so thank you, Anumaya, for your great presentation today and responding to some of the questions. If you have some time this afternoon, it would be great if you could respond to, to many other questions on Slido. With this, I would now close the first session, which gave you a theoretical introduction to satellite or dust monitoring with satellites. And I would now start the practical data discovery part, where we today focus on some of the satellite data Anumaya presented and introduced, how you can also work with them practically. Before we start, though, I would suggest again to have like 1 to 2 minutes, just like a break if you need to get some water or a short coffee. Or get up and have some movement before we then start. So it's now 10:06. I would propose that we start at 10:08. I will also open another poll because, and if you go to Slido, I would really appreciate if you could select the satellite data you're mostly interested in, which we should cover today in the practical session. So you see here the full list of satellite data. We prepared an example for you. So don't worry, all the examples will be there for you on the platform. But for the next 50 minutes, because we have 6 different satellite products, we could focus, I would say, on 3 of them to have a deeper dive into the products. Or if you say, oh, okay, I would like to have more like a general overview, but then to all of them in less detail. So then now 2 minutes of our time just to have a short break until we reconvene. I would suggest we start at 10:10. So yeah, then see you there. Okay, welcome back. You see already the poll is going strong. So we have a clear winner. So there is apparently a great interest in Sentinel 5P Tropomi aerosol index in the aerosol index product. And then I see like on third position, we actually have all of the above, but in less detail, and then also MODIS level 2 10-kilometer aerosol product. So we have a great interest in level 1 products and true color and dust RGBs, and then also in Sentinel 5P. What I suggest, we start with Sentinel 5P and go then on to the EUMETSAT second generation natural color and dust RGB, because also taken from the question and answers, there is a great interest in the dust product or in the dust RGB product. And then we can see after we covered MODIS and EUMETSAT second generation and Sentinel 5P products, if there is a bit more time, we could have a high level overview on the other products. But don't worry, on the training platform, you have access to the notebooks, and if you can also go through these notebooks in your own time today. And then if you have questions, we can also address these questions then in one of the next sessions, like tomorrow or like until Friday. So with this, I start here today our data discovery part. So welcome again, or welcome back to the second part of the training school and workshop on dust aerosol detection and monitoring. Just as a short reminder about the program of the data discovery part, today we are on day 2, and because we closely link the data discovery part with the part 1 during the webinars, we also introduce you today practically to some of the satellite data and products Anumaya introduced you to. And then at the end, we also will have another 5 minutes of questions and answers. So please, if you have any questions, go to Slido and drop your question there. What we focus here, or what we prepared for you in the data discovery part, are 6 different products. So we have examples how you can load, browse, and visualize level 1 RGB composites with a specific focus on the dust RGB from EUMETSAT. And we will also show you the fact sheet Anumaya mentioned, which really nicely introduces and explains how you can also interpret the dust RGB. And there we have 2 examples, like one on the EUMETSAT second generation and another example on MODIS RGB composites. Then we have 3 examples on aerosol products, which are level 2 data. So one is the Sentinel 5P Tropomi, the ultraviolet aerosol index, then the MODIS 10-kilometer aerosol product, and also the multi-sensor product, PMAP, which stands for Polar Multi-Sensor Aerosol Optical Properties, which gives aerosol optical depth as a parameter. And we have then another example of the absorbing aerosol index data from GOAM2 on board of METOP A, B, and C, which is an aggregated level 3 product. So these 6 examples are available for you on the training platform. And here you see just an example on how these products look like. So the RGB composites, this is here just the dust RGB, but the notebooks also contain quite a bit of information on how you interpret it. But as Anumaya already said in her talk, that basically the dust RGB, like especially the pinkish colors here, indicate like a high dust occurrence. But here you see also, because we have red colors, which indicate thick ice clouds. So most likely also the dust is just below the cloud here, and just in some of the parts where there's no clouds, we can really also indicate that there are dust occurrences. Then there's just an example of the level 2 aerosol products. Here an example of Sentinel 5P, MODIS 10-kilometer aerosol product, and also PMAP aerosol optical depth. And here we have another example of the GOM2 AAI index, which you see, which is already coarser resoluted, but which has the advantage that it is not dependent on cloud cover, and can also get information even though there are clouds. And so with this, I would now introduce you to the dust event, which we will focus on during the practical session from today until Friday. I will, hang on, I just wanted to also paste in the chat the Saharan dust event, which we focus on, because then you can have a closer look at the example. So in the chat, you see this web page, which is a science story from EUMETSAT on 5th of February. And this explains more in detail how METEOSAT captured a Saharan dust event at the beginning of February. And just as a background, we had from 5th to 7th of February, we had a stronger Saharan dust event impacting Europe, like the Mediterranean area in this phase, which also led to red snow in the Pyrenees, for example, or like very reddish and orange pictures from southern France in some cities, like from Lyon, for example. So you can have a look here. So you see here in the science story how this event started. You see here an example from MODIS, clearly indicating a dust plume coming from the Sahara going over the Mediterranean Sea. And you see here also an animation of the dust RGB, indicating here also like a strong dust plume going over the Mediterranean Sea here. So this is the background, and we focus on this dust event, and we prepared all the data examples and notebooks focus on capturing this dust event from different satellite sensors. And this example, or this dust event, will also taken forward to the next day. So we will then tomorrow focus on ground-based observations, and on Friday on model-based observations. With this, I would just remind you on how you can access the platform. So as I said this morning, so every day we will set it back to 0. There will be 100 spots available. And so even if you don't have a chance during the webinar today to go to the web platform, you will have another chance tomorrow to secure your spot. So you can go to login.ltpy.atomplatform.eu, log in with your account, and then just to make sure you go to training.ltpy.atomplatform.eu. And then you should be in the Jupyter Lab training platform, where we have our folder, which is called dust_workshop_part1. And today is the first of the data, really introduction to the data. And so the notebooks for today are under the folder 01 satellite-based data. And you can click there. And as we said, so let's just have a quick look again so it didn't change our poll. So we will focus on Sentinel-5P and the 2 level 1 products. No, the MODIS level 2 aerosol product. Okay, so we will focus on EUMETSAT 2nd generation level 1 and then also the MODIS level 2 10 kilometers. So in this folder, you have these 6 different notebooks. And the first one is the Sentinel-5P Tropomi Aerosol Index Level 2 product. And then with a double click, you can open the notebook. And we will focus on going through the notebook and showcasing you how the data is structured, in what format the data is coming. But you will also get like here quite a bit more interesting information about the data, which you can have a look. We also link to the official data documentation that you can also get additional background information of each data product and satellite information. So Sentinel-5P has the Tropomi instrument on board of the satellite, and which measures from this instrument we can retrieve a level 2 product, which gives us the ultraviolet aerosol index product, and this notebook focuses on this product. The data, the Sentinel-5P data, you can access via the Sentinel-5P pre-operations data hub. And we linked it here, and you can just log in with S5P guest and also the password S5P guest in order to retrieve and download data. The data are disseminated in NetCDF, and as we introduced you yesterday, NetCDF data is one of the common formats to disseminate satellite information after GeoTIFF, I would say. And with Python, there is a library called Xarray, which makes it very efficient and easy to also load and process NetCDF data. So we start with each notebook by loading some libraries. So you see that we load Xarray, Matplotlib, and Car2Py for visualizing the data. And we also make use of the functions library, which we introduced you yesterday, to make use of some of the predefined functions, especially for visualizing the data. So the first part is how the data is disseminated, and we were interested in opening a data file and to see how the data is structured. And so you with Xarray there is, so if we go to, let's go back one moment. So if you go to the data folder, so if you go one level back and you go to the data folder, there's also for each day one specific folder. So in the folder 1 satellite, you have a folder called Sentinel-5P, and there are two Sentinel-5P AI files available. If you have a look on the information the data file provides you, is that you see here one file is for the 6th of February 2021, and the other one is for the 22nd of February 2021, because there were actually 2 dust events in February over Europe, but we will focus on the first event, which occurred between the 5th and the 7th of February. And so we focus on this file. So we open the file with Xarray and with the function open_dataset. We specify here the link or the path to the file. And important for Sentinel-5P data is that we have to specify a keyword argument, which is called group product. And this group or this keyword argument allows us to load a specific group of the NetCDF file, because the Sentinel-5P Tropomi data are organized in 2 groups, in product and in metadata. And in the product group, we find the main data fields of the product, like also including latitude and longitude information and the data and the variable itself. And in the metadata group, we get additional metadata for the data itself. And so we specifically interested in the product group. And if we, so you can execute this cell, and oh, I haven't loaded the libraries. If we execute it, then we load a data set. We have quite a few dimension information like scan line, ground pixel, time, and corner, and also quite a few data variables. So we see here the aerosol index at different wavelengths, and delta, time UTC, and also a QA value. And so we see that the data product or the object, the data set contains 4 different dimensions. So scan line, ground pixel, time, and corner, and then also specific data variables. And the next step is to probably load a data variable to better understand what information the aerosol index provides us. And so we could, for example, load the aerosol index from 354 to 388, but also feel free to make here changes and also load a different aerosol index with a different wavelength window. So for the example here, we load the aerosol index between 354 and 388. And as yesterday indicated, we can load a data variable by specifying the name of the variable in square brackets. And this is what we do here. And if we retrieve or reload from the data set the specific variable as data array, we see that our data array has now 3 dimensions, like the time, scan line, and ground pixel. And so because we only have 1 time information, which is for like for 1 day on the 6th of February, but we also see like scan line and ground pixel information, which we make use of to visualize and plot the information. And then we can retrieve just the 1 index, like the time information, because we only have 1 information here. So we can actually reduce this information by specifying the index 0. And if we do this, then we have the information, or we have our data array for this specific time and our scan line and ground pixel dimensions. Additionally, as also indicated yesterday, once we loaded a data array, we also get additional metadata information regarding to units or the long name. So this helps us to better understand or get additional information about our variable. So we see, as Anumaya said in the morning as well, that it is actually unitless. So we don't have a specific unit for the aerosol index. And we also see here, again, like the wavelength window for this aerosol index, which we just loaded. And we can make use of this information, and we can store it as variables, like a units variable and also long name variable, because this information is actually very good to also be or to bring it forward for visualizing. So instead of us defining a title or the unit, we can actually make use of this information. We store it as variables, and later on, if we create our map, we can then make use of these variables which we defined here. And then we are actually already in a state. So we loaded our data array. We have our data information with scan line and ground pixel information, and also latitude and longitude, and also long name and units. And we are now in a state that we can actually load or visualize the information. And with this, we make use of the function, which is part of the functions library, visualize p-color mesh, which combines two Python packages, which makes use of the matplotlib, which is the Python visualization function, visualization package. And one of in this package, one of the function that is offered is called p-color mesh to visualize two-dimensional maps and two-dimensional data. And we also combine it with Cartopy, which is a very powerful library to show different data and different geographic projections. And we linked all the so we also linked all the Python packages, so you can also have a closer look to the Python package itself. Just a reminder, especially because you haven't worked with these predefined functions before, if you add a question mark and then the name of the function, you can open the function's docstring to see what key arguments are needed to prepare a plot. So just as a reminder, if we execute this here, then you see that all these keyword arguments are needed in order to be able to visualize the Sentinel-5P aerosol index data. And this is what we do in the next step. So we specify all the keyword arguments here. So we provide our data array, which we loaded above with our variable aerosol index between this for a specific wavelength window. And from our data array, we also take the longitude and latitude information from the data. We specify a projection, and this projection comes from the Cartopy library. So there is also an overview of different projections you can play around with. But here in the example, we want to have a plate carré projection. We define a color scale. So the example here gives us a color scale from red to yellow, and this R specifies a how do you say, like it's changed. So usually it's going from red to yellow and indicating the highest numbers are indicated as yellow. And with this, we just reverse it. And and this means that like lower values are shown in yellow and higher values are shown in red. And then we make use of our variables here, like the units and the long name. And at the same time, we also make use of the time information, because then our title of the plot also shows the time for when the data is valid. We define here minimum and maximum values of the index. And here we want to showcase global information, but we could also, in the next step, we also show how we can actually make a geographical subset. And with this, if you execute this function, oh, I didn't run this cell. And if we then run it, then you see the specific plot that you see here. It is specified because we just selected a path which was covering over Europe. So yeah, like you see some of the values here, but we're specifically interested in Europe because the Saharan dust event majorly affected Europe. It would be good maybe to zoom in and to create a geographical subset for Europe. And so in the next step, we create a geographical subset. We also have a function in the functions notebook, which is called generate geographical subset. Here again, we can also load the docstring, and we see that we have to define the latitude and longitude minimum maximum bounds, and also the X array, which we want to geographically subset. And then there is also another keyword argument, which is optional if you want to reassign the longitude values to and shift the values from 0 to 360 to -180 to 180. And this information is just of interest for model data, which we will come back on Friday to it. So here we define our bounding box information for Europe, and we can execute the cell, and then we can apply this function. And again, we just apply the keyword arguments that are of interest. We want to subset the data array, which we loaded at the beginning, which is the aerosol index data array from our data set. And then we specify the function, our data array, and then the latitude and longitude minimum and maximum bounding box information for Europe. And the subset, if we look at it very clearly, so if we go back to see of the size of our data array before, we have over 4,172 pixel information along the scan line, and 450 ground pixel information in our original data file. And once we subset it, if we go back to our subset, we now see that we still have the same ground pixel information, but our scan line decreased to less than 1,000 pixel information. And so this means we have now our geographical subset. And with this, we can then now visualize our geographical subset. We again use the same keyword arguments, just with the difference that now we set the keyword argument set global to false, and then we just specify the bounding box information here to also set here the minimum and maximum bounds of our subset. And but then here again we apply the function here, and if we then execute it, then we see a geographical subset of the Sentinel-5P aerosol index information. And here you see very nicely like strong high aerosol index values over the Mediterranean Sea, but also very high values on the 6th of February in the Alp region in northern Italy, and also in Switzerland. So this is an introduction to Sentinel-5P, and I would now go to the second data set which was voted, which is the EUMETSAT second generation level 1 RGB composite. And with this, we can go back to our folder here on the left, to our Dust Workshop folder. We again go to satellite-based data, and then we open the notebook number 14, which is called EUMETSAT or MSG Dust Product Level 1. And if we double click on it, we open the second notebook, which focus on the MSG. It's like the natural or the true color and the dust RGB. So I just check if there, so yeah. So probably I propose that we continue introducing the three data notebooks, and then we can go to some questions in case you have questions. So the EUMETSAT second generation is a satellite constellation which have the Severi instrument on board, and they offer and EUMETSAT, and this is operated by EUMETSAT, which offer a called 0 degrees service, which provides the METUSAT second generation data almost in near real time every 15 minutes. And this notebook shows you how you can load and browse and visualize the data with a Python package called SatPy. And this allows for a very efficient handling of data, especially from meteorological satellite instruments, including Severi and MODIS, because the data is disseminated in a specific format for MSG data, which is called in a .NAT format. And so the SatPy library helps us to efficiently handle this data format. Again, this notebook features the Saharan dust event, which impacted Europe on the 5th to 6th of February. And you see here again, like additional information. So as I said, it's like every 15 minutes since 2004. It doesn't cover the full globe, as Anumaya also indicated in the morning. But yeah, its strength is really like the high temporal resolution. And here is also the example how you can download the data. So the data is available in EUMETSAT's data store. If we click on it, then so the example here, we already linked a specific example like to the high rate Severi level 1.5 image data. But of course, if you go, I think here, this is like the new EUMETSAT data store, where you can also look for other data. But for here, you can specify here the day you're interested in, and also the time. So let's say for today and for yesterday, if we just look for results, then you get in principle like every 15 minutes a data file which you can download. But you see already that these files, like one file is quite heavy, but at the same time you also see here also the geographical region that is covered every 15 minutes. And so for our case study, like especially also monitoring Saharan dust events and also the event that impacted Europe, it is well covered in the geographical coverage of METUSAT second generation. And then we again start with loading our Python packages. We load here, you see here specifically some additional libraries or functions we need. So we need a scene class, composites, writers, and resample from the SatPy package, and additionally also a library which is called PyResample. And then we can also make use of the helper functions, and then we can start loading and browsing the Severi level 1.5 data. And because the data is disseminated in the native format, we can't use X-array, but we can use the Python package SatPy because it supports quite a large collection of different readers of specific data, meteorological satellite data products. And so the function or the function available _ readers of the SatPy package allows you to also get an entire list of all the available readers SatPy offers. And for the METUSAT second generation, we would need the readers Severi _ level 1B _ native because the data is disseminated in a native format. But you see here like already a very long list of all the formats that are supported by the SatPy package. And so from the EUMETSAT data store, we downloaded for several hours for several time frames for the 5th and 6th of February the images. You can, let us just go quickly, also go to the data folder again, and then to satellite, we have here a folder called EUMETSAT. And then if we go to event, you will see here a list of different EUMETSAT Severi data files. And here in the data file, we again see the timestamp of the specific data file. So for the example here, we have this file is valid for the 5th of February 2021 at around noon at 12:12. And then we have another one for hour 13, for hour 14, for hour 16. And we also have here for the 6th of February for several hours, one file too. And this is also an opportunity for you where you can also try out linking to a different data file and also see how the dust and true color RGB changed for specific, for different hours. Because, for example, on the 6th of February, towards the later evening hours, it was very hard actually to indicate or to specify or to see the dust event because we had just too many clouds. But on 6th of February in the morning, we will show you one example where we actually see the dust event quite nicely. So this is also for you an opportunity that you can actually change the timestamp of the data file to get a feeling of the dust RGB and the true color RGB. And here, so we select one file as a list. We can do this with the Python library glob, and the SatPy package needs a list of the data file. And so here with these asterisks, we just indicate the timestamp we're interested in. And so here we load on 6th of February 2021 on at around 7 the file. And then we have this list of one file we want to load. And then in the next step, the SatPy library requires you to construct a scene object. And you can do this with the scene class. And we specify the reader of our data, which is the Severi _level 1b _ native, and then the file name, which we specified here above. And once we did it, we have a scene loaded, and then we can browse what the scene contains with the function available _ dataset names. And if we do this, then we see that our scene object has all the channel information of the EUMETSAT 2nd generation, like in the visible, infrared, in the visible and infrared channels, and in different wavelengths. And so you can use the function load to specify one specific band or channel information. So for example, we just specify here the infrared at 10.8 wavelength. And if we then open it, so first you have to open a channel information, and then you can specify the channel information by specifying the name of this specific band. And once we do this, then you see the underlying constructor is actually also a X-array data array. And this gives us a lot of flexibility, because with a data array, we know how to handle a data array and also how to visualize it. And then we can actually use it as a specific data array. So we, for example, can use the attributes function and keys to better understand what key information our data array offers, to browse additional information. And also we have here, for example, we can get here the start time and the end time But for now, so this is just like showing you how you can actually get how you can load an image and how you can then also get more information about the image, and you can also do some composites. But because we want to focus on predefined RGB composites, we just reload our scene again, because we're not interested in a specific band, but we are actually interested in predefined RGB composites. And the SatPy library gives us already predefined IDs for specific RGB composites to highlight specific events and phenomena. And one of these, or some of these IDs are, for example, natural color, snow, or dust. And with the function available _ composite IDs, you see a full list of all the predefined RGB composites that are available. So for the first step, let's open the natural color one. We again specify the composite ID we are interested in, so natural color, and then we load also the natural color composite. And what this ID is doing, in the background, SatPy already knows which channel information it has to take in order to create this RGB composite. We can specify an additional keyword argument upper right corner, because per default, the scenes are loaded with the North Pole facing downwards. And if we want to bring it to a format that the North Pole is facing upwards, we have to specify this keyword argument. And then we can load it. We can use the command print. And if we print our scene object, we see that we have now a data array with the natural color composite loaded. And the next command I don't execute because this will take a bit, but this shows with the function show, you can basically get a very nice visualization of the entire globe of your specific scene. So this afternoon you can also try it, but just be aware this just takes a bit to load the entire globe, but this is a very nice visualization. So the next step, we want to actually generate a geographical subset for Southern Europe, and we can do this by applying the function crop and specifying a bounding box with the latitude and longitude information. So we specify our bounding box information for the part in Europe over the Mediterranean Sea we want to focus on. And then we want to show our natural color composite, which is part of our scene object, and we apply the show function. And if we execute this, then it also takes a bit, but we then see a geographical subset of our image. And this is the first visualization where you already see that here we have a strong dust intrusion over the Mediterranean, but at the same time also during this time already quite strong cloud cover over northern Italy and the northern part of the Mediterranean Sea. And then from this cropped image, we can also load additional area information. I just go through it because we don't have too much time again, but you can go through it. We show you an example how you can actually retrieve also X and Y values in meters, because this is actually the native or the original projection unit. And with this X and Y values in meters from the nadir, we can then basically store this information and crop it as well, and resample the information. And this is important actually to use the to crop the image and resample the image with the original projection unit. because of the satellite angle view. So in our subset, it's not distorted as much, but the more north we could come, the resampled image could be quite distorted if we crop it with just simple latitude, longitude information. And so that's why we also show you how you can actually crop it with X and Y information, and how we then also store the area information from our cropped image. And then this area information we can apply to the we can use the function resample, and we can make use of the area coordinate reference information here to resample our image, and then we can show it again. And then in the last step, I would probably now go to the next step to showcase you just the dust RGB. So I just want to show you here the section 4 also shows you how you can actually visualize these images like as with CartoPy features. And so this would then basically allow you to add additional country borders, so, and also a grid information to also enhance maybe the signals a bit more. I will not go into detail here, but you can have a look how this can be done for yourself. And then in a final step, we actually also would like to have a closer look to the Severi dust RGB composite. Here again, we load our data, and we load here, we specify the dust RGB, and again we load the dust RGB, and then we can resample it, and we can actually make use of the area coordinate reference system which we just defined above. And so we resample it to the same area. And then in the last step, we can actually visualize for the same time and hour. So for 6th of February, around 7 in the morning, we can show our dust RGB composite with strong indications that we have here dust impacted or coming from the Sahara over the Mediterranean, and also here below the clouds we have really strong dust signals, what we see here. There is also what we said here, the Severi dust RGB quick guide. This is also what Anumaya referred to, which gives you a very nice comprehensive explanation of the dust RGB. It also helps you to interpret the colors and really tells you what color signals what information. So this is really, if you're interested in this RGB, then just go right at the end, and there is this quick guide which helps you to interpret the dust RGB. In the remaining short time, so if you don't mind, we maybe go a bit 10 minutes longer. I would just open or go quickly through the MODIS aerosol product. And here again, we go back to the dust workshop, the satellite-based data, and then under the notebook 15, this introduces you to the MODIS aerosol product level 2. And here again, we give you an information. So the spatial resolution is around 10 kilometers. It has a global spatial coverage. And we also linked or give you indications how you can actually get or retrieve the data set, but you have to register for an Earth data account. So this is actually quite straightforward. So here we load libraries, but we make use of the Python library PyHDF because the data is disseminated in HDF4 format, and the Python package PyHDF is very efficient in handling HDF data files. And so the first part is to load also for the 6th of February the HDF file, we specify a scientific data set, which you can specify with the SD constructor. And then we read it and we specify a scientific data set. And then we specify the variable we're interested in, and which is optical depth, land and ocean. And with the function select, you can select the data set name, and then we can also we can read it as a two-dimensional array with the type double what you see here. And then we, if you specify it, we have a NumPy array containing the information. And the next step, we do the same for loading latitude and longitude information. And we also store those as two-dimensional arrays. For latitude and longitude, as an example, you see here, it's also a NumPy array containing the latitude information. And then additionally, we can retrieve also attributes which are coming with the data file. So we can specify the global attributes, and from these global attributes, we can retrieve long name information, units, scale factor, and offset. And this information we need to actually also, so especially offset and scale factor, to apply to the data in order to actually get the real value of the data. And so this is what we specify here. And then we replace all the data which have the value -999 with none, because this is just a fill value with where we don't have data information. And here we apply to the data, we subtract the offset and we multiply it with the scale factor. And the result gives us the real value of the data of the aerosol information. And then we can visualize the optical depth also with the function visualize p color mesh. We specify here again the keyword arguments. So we use our data information where we applied the offset and the scale factor. We use the longitude and latitude information. We apply the protection plate carré again. Here, color scale, you can feel free to also play around with it. We use the units attributes and the long name, and also minimum and maximum range of the color range. And we specify longitude and latitude maximum and minimum bounding box information. And if we visualize it, then we see here also the aerosol optical thickness or depth product also shows very high values over the Mediterranean Sea for some parts, especially like for cloud-free parts. But here you see also that in some parts where we had clouds, we couldn't get or the instrument doesn't, or the product doesn't get information on aerosol optical depth. And with this, I would close now the practical data discovery session. As we said, like this here, all the content is available for you, and it's also really this week, it's available for you also to browse for yourself in a self-paced manner. Feel free to drop any questions on Slido also this afternoon if you have specific questions to the practical part on the data. And we will regularly monitor the Slido and also can respond to your question asynchronously. Also, if you're not live during the training workshop. So I would have a look to if there are some questions to go to the question and answers. Let's close this poll. And I don't know if are there any questions? I just probably have to go to the most recent ones. Okay, so okay, so there is one question on if I have changed the codes inside the blocks, can I restore the codes again? So yeah, so basically it depends where you are, so where you are working. So you have this, if I go back to the training platform, as I showed you yesterday, so if you work directly in this folder and you, let's say you opened, I just closed this one, and you opened a notebook in this folder and you made changes to it, for today, it will not be restored, but until for tomorrow, you will get a fresh version again, and it will be restored to our version which we provided you. If you want to make sure that you always have this as a reference, I propose you to duplicate the notebooks to your own working space. And so you can, for example, like with the right mouse click, you can copy this notebook and then you can go to your working directory and then you can paste the notebook here. And any notebook you open here, this is your working version. It's a copy, you can make changes, but you will need to also adapt the folder passes here. So for example, the data folder, you will need to add an additional layer because we are now outside of this Dust workshop. So we have to go to the Dust workshop and then to data, and then it should be loaded. So this is, so you will need to, and also the functions notebook, we have to go to here to the, so you will need to, if you do this, you will need to adapt some things because you're outside of this folder, but then you're safe and you can make any changes, and you will still be able to have a look on the original version. Okay, then yeah, Michael is asking which Python packages do you use to resample polar orbiting satellite data to a regular grid so you can run daily comparisons? Yeah, this is a very common question asked, especially for Sentinel-5P data. So there is an option to bin or to grid, to bring Sentinel-5P data on a regular grid, and we also have an example how to do it. So in the end, we don't retrieve the data, the Sentinel-5P data from the Sentinel-5P hub, but from the Amazon Open Data data program, because there we have the data already in a daily aggregated format on a global scenes. And with this example, we retrieve the data in GeoTIFF, in cloud optimized GeoTIFF, and then we actually have a code with XArray how we also brought it into a regular grid. And if okay, I will respond on Slido with some links to some example notebooks where you can have a look at it. And I don't know, Michael, if you're also part of the practical workshop next week or the week after, we can then also readdress it again. And we have then much smaller groups. And if you're interested in this, then we can also highlight this example in one of the sessions. But I will link some example notebooks that you can see how this could be done. Then I don't archive this for now, and I highlight this one. Is there a suitable choice of colors that should be used for dust aerosol maps? Some sources suggest not to use rainbow. Yeah, this is just also like a personal view. Rainbow or spectral is often not the best choice, especially also if you want to address color blindness. That's why these ranges are people tend to not recommend them. There are a set of different color ranges. So we linked it in one of the notebooks also, like have a look for Matplotlib color range, and then you see different color ranges. And in the end, it's also probably up to you what you feel like looks best. You often see for dust and aerosol maps something reddish, oranges, yellowish. But CAMS, for example, has their custom color scale. And so, yeah, it really depends also. It's probably a personal choice, but rainbow and spectral is often not used because in order to address color blindness. Then, so how will one get to the data website as shown by you during the presentation? I guess you mean, for example, this data website. So all the websites I showed you are linked in the specific notebooks. So like, for example, Sentinel-5P. So each of the notebooks has a section at the beginning how to access the data. And here we linked all the data web pages where you can get the data. So for Sentinel-5P, we link the Sentinel-5P pre-operations data hub, for example. The EUMETSAT data store where you can get a EUMETSAT second generation is linked in the notebook for the EUMETSAT second generation. And there we have also a section how to access the data. And then you can go here to EUMETSAT data store and you get to this data page. So the information is on each notebook that you should find your way to access the data. Okay, we had this one. If you specify maybe on Slido which missing values you are referring to, then it would be, then we can respond like Sentinel-5P data or others, then we respond offline. So I would suggest I take another 2 questions and then we would close the session for today because we also don't want to take too much of your time. Or we also don't want to go much over time. We will meet again tomorrow and we can then address offline any remaining questions and also tomorrow during the practical session. Okay, so I think there's one question. What does the specifies value in? So this is also if you specify what data you're referring to, then we can respond to this question in offline. And then I probably highlight this one. Is there a script available to handle multiple MODIS level 2 AOD files for seasonal or annual climatology of AOD? No, so we don't provide it as part of the data discovery. So because we only focus on introducing you to MODIS level 2. If we go towards seasonal and annual climatology of AOD, we show you we have also a notebook on the GOME2 level 3 data, which are already aggregated products on monthly and daily scales. And so this is so we don't showcase you specifically how to handle climatology, but for the practical workshop next week, we will have one example to analyze more the seasonality or the annual cycle of AOD with GOME2 products and also model data. So there will be some examples, but here we would need to go from the level 2 to actually level 3 to the level 3, which means it is on a regular grid aggregated products on daily or monthly resolution, and then we can actually go to analyzing climatologies, but then we would also need a longer time scale, and we don't provide this in this data discovery part. And so I would propose now to close the session. As I said, we go through the questions on Slido and we respond offline. I would thank you to also come or to join us this morning again, and to listening and even staying longer. And thank you, Anumaya, for your very great introduction and presentation also this morning. And then I look forward to seeing many of you again tomorrow. And tomorrow we will have a similar setup. We will have the first hour. We will focus on a theoretical introduction to ground-based observations. And then the second part, we focus again on discovering data related to ground-based observations. And with this, thank you again for joining, and I wish you a nice remaining day, and hope to see all of you tomorrow again. Bye.